This video presents our article, Geometry-Aware Onboard Perception for Powerline Conductor Estimation and Outside Field of View Tracking During Close-Range Flight. During autonomous close-range flight within a powerline corridor, the drone must maintain pose estimates of the conductors for safe navigation. Only a subset of conductors might be inside the sensor's field of view while others may be outside. The onboard sensors can detect the in-field of view conductors while the outside field of view conductors become subject to drift during GNSS and IMU-only tracking. This paper presents the relative cable positions algorithm. When multiple conductors are visible, their positions are tracked using independent Kalman filters within the plane orthogonal to the powerline direction intersecting the current drone position. The algorithm computes the relative positions between visible cables and applies moving average filters to apply smoothing to the translational vectors. Later, when previously visible conductors exit the field of view, the algorithm can reconstruct their positions from remaining visible conductors and their estimated relative translational vectors. This anchors pose estimation of invisible conductors to the estimated positions of visible ones. The RCP algorithm builds on top of previous work by the authors within onboard powerline perception. The full perception system relies on onboard fusion of millimeter-wave radar point clouds for detection of conductor positions and RGB camera images for derivation of powerline direction through the Hoff transform. Flight tests were conducted with the RCP algorithm enabled and disabled without RTK, as well as with RTK enabled and RCP disabled for a clean comparison to high-precision tracking without RCP. The drone was flown manually in paths with all conductors initially within field of view, then each disappearing and later re-entering the field of view of the millimeter-wave radar. The three views show a representative flight for each configuration with perception data overlaid, scaled in perspective by best effort. The videos are independently scaled in playback speed adaptively to align exit and re-entry events of conductors in the millimeter-wave field of view. Disappearance of conductors from the field of view of the millimeter wave is indicated by the sphere becoming red. Invisible conductors' positions are estimated from the stored relative cable positions for RCP, while for non-RCP estimation relies fully on GNSS and IMU-derived inertial odometry. The jumps in conductor position estimates at the reappearance events are recorded for each configuration and compared to quantify outside field of view tracking performance using RCP over non-RCP odometry-only tracking. RCP is shown to decrease outside field of view position estimation drift by up to 59%, averaged over the experimental runs, measured in reduction in re-entry estimated position jump magnitude, while the RTK baseline as expected beats RCP. This shows the potential for RCP in applications targeting autonomous close-range drone flight within powerline corridors, such as for inspection and maintenance operations. Thank you very much for watching.